Welcome everybody. This video is going to be your lesson for 13.4, which is about rational and irrational roots. So now what we're going to do in this section is basically find all the zeros or x-intercepts or roots of a polynomial. Whereas before you had usually some information, like you had a cubic and you knew one of the roots. So then you could divide and then get a quadratic and find the remaining roots from there. Now we're going to start from scratch, meaning we have a polynomial and we don't know any of the roots, and this is going to give us some light, or shed some light as to what we can do to find some of those roots. Okay, so we'll start with the rational root theorem. And the key here is that you remember what the word rational means. Okay, so if there's any rational roots, meaning integers or fractions and things like that, then this is where they're going to come from. Okay, so given any polynomial with integer coefficients, and what we mean by that is a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on, all the way down to a1x plus a naught. So, standard form, n is your highest exponent, that's the degree of the polynomial, and then all your a's are just coefficients. So a sub n minus 1, and all the other ones, a1, a sub 0, they're all integer coefficients. Okay, so given any polynomial that meets these conditions, if there are any rational roots, we'll call those p over q. So if p over q is a rational root of this equation, then p is a factor of a sub 0 and q is a factor of a sub n. Hey, I'm actually making a video right now. Yeah. Okay. All right, so where was I? All right. So if there's any rational roots for a polynomial, and we'll look at an example, then those rational roots have factors in the numerator that come from this last number, this constant a0, and that rational root possible factors would have been from the leading coefficient, which is a sub n. So that's what we mean by p's and q's. Your p values come from the last number here, and your q values come from this leading coefficient here. Okay, so for example, if we have 2x cubed minus x squared minus 9x minus 4 equals 0, and we want to find all the zeros, then we have -4 and 2 as our p's and q's. So we're going to write down all the p values, which again are just all the factors of this last number. So if you think about 4, 1 goes into 4, 2 goes into 4, and 4 goes into 4. And we do everything possible, so we list plus or minus 1, 2, and 4. Doing the same with 2, the factors of 2 are plus or minus 1, plus or minus 2. Now your possible roots are all your p divided by q values. So you just take all your p values and divide it by all your q values. So 1 divided by 1, still 1. 1 divided by 2 gives us a half. And then we go 2 divided by 1 and 2 divided by 2. 2 divided by 1 is 2. 2 divided by 2 is 1, so I'm not going to list that because I already have it here. 4 divided by 1 is 4. 4 divided by 2 is 2, but I already have that, so again, not going to list it. So these are all the possible rational roots. So if this polynomial has any rational roots, these 8 are the only possibilities. Okay, so what we do now is synthetic division to check. Okay, and what I generally do is start with the smallest positive value, smallest positive root, and I'll explain why in the next theorem. So I'm going to start with 1/2 and then see if this is a root. Okay, so when I do that, write down the coefficients: 2, -1, -9, -4. Bring down this first number, you get 2. 2 times 1/2 is 1. Then you get 0. 0 times 1/2 is 0. You get -9. -9 times 1/2 is -4.5. This doesn't work because we get a remainder of -8.5. Okay, maybe I'll do -1/2 now. So I'll do same thing, check with synthetic to see if -1/2 is indeed a root. 2 times -1/2 is -1. Add them up, -2. Multiply, you get 1. Add, you get -8. And you get 4. When you add, you get 0. Okay, so remember, this means that there's a remainder of 0, which then means that whatever we have here is the other factor. So using the linear factors theorem and the division algorithm, just this part here leads us to say that 2x cubed minus x squared minus 9x minus 4 can actually be factored, since -1/2 is a root, as x plus 1/2. And then the other factor would be this quadratic that's left over, which is 2x squared minus 2x minus 8. Okay, so if you have to find all the roots, we already know that -1/2 is a root. So now what we can do is just factor this polynomial. Take out a 2. You get x squared minus x minus 4. Looks like this is not going to factor, so you're going to use the quadratic formula. And you'll get x equals 1 plus or minus the square root of 17 all over 2. So these are the other 2 roots. So your roots are going to be -1/2 and then 1 plus or minus root 17 all over 2. Okay? So again, rational root theorem gives you ideas as to what possible rational roots any polynomial would have. And right now it is basically trial and error, but we're going to try to tighten things up a little bit so that you have more of a systematic approach, so that you're not just blindly checking all these possibilities. Okay? But hopefully this gives you an idea of what's going on. Find your P's and Q's, test these values, see which ones give you roots, and then take whatever you have left over and then see what you can do with that. Either you keep checking for more roots, or maybe if it's a quadratic now, you can use the quadratic formula or factor some more, and then you can find the other answers. Okay? So let's talk about the upper and lower bound theorem. Upper bound, lower bound theorem. And, basically, instead of making this official, I think I'll just cut to the chase. Let's say you're doing synthetic division. So if you're dividing synthetically, you have a couple of scenarios. Let's say you're testing a positive number here. You know, and you bring down this number and you divide synthetically. Okay, so if you're testing a positive number and when you do that, you get a positive, meaning that these are all positive, then what that means is that there are no rational roots that are higher than this positive number. So we call this an upper bound. And all that means, again, upper bound means that this is the highest, that there's no number that's going to be greater than this number that would be a root. Okay, and we can do something similar. If I'm testing a negative number synthetically, and we do the procedure, and we get in this third row plus, minus, and so on, or minus, plus, minus, plus. Okay, in other words, our answer alternates from positive to negative or negative to positive. Then we know that this number that I just tested, we call that a lower bound because there's not going to be any number that's a root that's lower than this number that was just tested. Okay? So I'll illustrate with an example so you guys kind of understand what this means. Okay? One thing that we should know going forward is that 0 counts as either positive or negative. Okay, so for example, up here, if you had 3, 0, 2, we would say that 0 is positive. Okay, or down here, if we had a positive, a negative, a positive, and then 0, we can count 0 as a negative as well. Okay, so 0 will work to our advantage whenever we have it show up as part of the answer in the third row here. Okay, so how does this help us? Well, it gives you more of a systematic approach. Okay, sometimes you might just want to know where the possible rational roots are located, between what numbers. Sometimes you can use this, for example, back up here. I know it didn't happen, but let's pretend that it did. If I tested 1/2, which is a positive number, here I have a positive 2, and again, 0 can be positive, so I'll count it as positive. And let's say these last two numbers were both positive. Okay? Then I would know that 1/2 is a wall. There's nothing further than 1/2, greater than 1/2, that it's going to be a possible root. Rational root, anyway. So what that means then is instead of testing 1 and 2 and 4, that I don't have to check those because this proves that there's nothing greater than 1/2 that would be a rational root. Okay? Now I'll illustrate how to find the lower and upper bounds with an example. So let's say we have a polynomial x to the 4 minus 3x cubed plus 17x squared plus 16x plus 20. Okay? And we want to find all the rational roots. Well, first we find our p's and q's, just like we did before. So for p, we look at 20, we write all the factors down. So that's plus or minus 1, 2, 4, 5, 10, and 20. For q, it's the leading coefficient here is 1, so the only factors of q are plus or minus 1, which means then that your p over q's, when you do all the possible combinations, are really just going to be all your p-values. Okay, so these are all the possible rational roots, which means that if this polynomial up here has any possible rational roots, that these are them. So we have 6, 8, 10. We have 12 possibilities here. Okay, so here's that systematic approach I was talking about earlier. First, let's start with the positive roots, or the positive numbers, seeing if that sheds some light. So I'll start with 1 and work my way up and see if I bump into anything. And we're going to, again, divide synthetically. So bring down the 1, multiply, add, multiply, add, multiply and add. Okay, almost. And by almost, I mean that we almost had all positives here. This negative here doesn't do anything for us. So all this shows is that 1 is not a root because it's a remainder of 51. And 2, that there could be possible rational roots greater than 1 because of this negative 2 here. Okay, so we'll keep checking. So now we go up to 2. And again, multiply and add and repeat. So we get 1, negative 1, 15. Same scenario. 2 is not a root. And this negative throws things off, so I don't know anything really. Let's go to 4. Multiply and add. Looks like this one is going to have an even bigger remainder. However, here's where the upper bound part of the theorem helps us. Here we were testing a positive number, and our answers were all positive coefficients. So right here, what this means is that 4 is an upper bound, which means that there's no roots that are rational that are higher than 4. So we're not going to waste our time and check 5 and check 10 and check 20 because this proves that there are none that are bigger than 4, that are rational anyway. Okay, there could be irrational roots like root 17 or 1 plus root 21 or something like that. Those are bigger than 4, and those could very well be roots. But this is just for rational numbers. So right now I've exhausted all my positive possibilities. I checked 1, I checked 2, I checked 4, and then here at 4 I can stop because of the upper bound theorem. So I don't have to check 5, 10, or 20. Okay, so let's work with the negatives now. So I'm going to check negative 1 and see what happens. Maybe it's a root, or maybe I figure out that there's no way that there's any roots that are lower than negative 1. So divide synthetically, multiply and add. Okay, so 25 remainder, but notice positive, negative, positive, negative, positive. These alternate, and that's what the lower bound part of the theorem says. So this means that negative 1 is a lower bound. Okay, so what we conclude is that from the lower and upper bound theorem, that if there's any rational roots at all, they have to be between negative 1 and 4, because negative 1 is the lower bound and 4 is the upper bound. Okay, so if they're asking you to find all rational roots, well, here you're going to say there are none. There are no rational roots and sometimes that'll happen. And because we have proven that if there are any rational roots at all, they have to be between -1 and 4. But we've already checked. We've checked everything between -1 and 4. So since we checked all possible rational roots from -1 to 4, we conclude that this has no rational roots. Okay? So what does this mean? That means that the roots for this equation are irrational, or could be irrational, like ones you would get from the quadratic formula. Or maybe they're all complex and imaginary. Okay, and without a calculator, we really can't do much. Okay? All we can say is if there's any possible rational roots, we start by writing out our P's and Q's, we start checking, and then using the lower and upper bound theorem, we kind of narrow down the search here. Okay? All right. Last, I guess I could add, because I'm not going to do a ton of examples. So this example that we just worked on here, there very well could be a problem where, again, you have to find all rational roots, and maybe there are rational roots. Okay? So you would do the same thing we did here. Maybe you get to a certain point where you get a positive number and all positive numbers here in the third row. So what this theorem does for you is it proves that there's no roots higher than 4, so then you don't have to waste your time checking for other roots. So not only will it prove to you whether or not there are any rational roots at all, but it'll also help you systematically check what roots might work and what roots might not. Okay? All right. Last theorem. It's called the location theorem. If f of a and f of b have opposite signs, then f of x has at least one real root in the interval from a to b. Okay, so I'll show you visually and from a table what this looks like and why this is a pretty obvious theorem here. So let's say here we have a table of values for f of x, and it looks something like this. Okay, so what the location theorem says is that if there are two values for for y, essentially, which is the same as f of x, and they have opposite signs, right here and right here. See how it changes from positive to negative? Okay, then what that means is that there is a real root between -1 and 0. Because -1 was the x value that gave us 6, and 0 was the x value that gave us -1. So if you actually graph this, you know, -2, 3, -1, 6, 0, -1, 1, 2, 2, 4, maybe the polynomial looks something like this. who knows what it looks like. But right here, at -1, if you zoom in close enough, you can see that it hits the x-axis, right here. Somewhere between -1 and 0. And if you look carefully, from here to here, we go from positive to negative and then negative to positive. So we've gone from a negative to a positive value, which means that it has to go through 0 another time. I mean, this makes perfect sense if you think about it, because you're not going to change from positive to negative or negative to positive without going through 0, which is exactly what a root is. So if you look at the two values, between -1 and 0 we have a root, and between 0 and 1 we have a root. And right here, here's 1, 2. Here's another spot where we have another root or an x-intercept or a 0. Okay? So this is what it would look like from a table. We can do another quick example here. I mean, it's a pretty basic idea here. You can see that from 0 to 1, here we have a positive value for our function, here we have a negative value for our function. So we know that there's a root between 0 and 1. Because at x equals 0 it's negative, at x equals 1 it's positive. And if you look at the graph, here at x equals 3 we're positive, but now where x equals 4 we have a negative value. So another spot where we have a root is between 3 and 4. Okay? Alright, so that's the lesson for tonight. Tomorrow you will come in and you will work on the practice problems from the packet. Farewell.